Think about a summer when you were maybe 8 or 9 years old. It felt like it lasted forever. Endless afternoons. A slow, syrupy crawl from one birthday to the next. Now think about last year, the one that actually just happened. It's probably already a blur. A couple of holidays, a birthday, maybe one big thing that happened, and then it's just gone. Same 12 months both times. Completely different experience of time. That's not you imagining things. It's not just getting old and forgetful. There's an actual mechanism behind it, several actually, and once you see them, you cannot unsee them. There are 4 different explanations scientists have proposed for why this happens. They're not really competing with each other. They are 4 different lenses on the same strange fact. Your sense of time isn't a clock ticking somewhere in your head. It's something your brain builds. And it turns out it builds that sense differently depending on how much life you've already lived. We're going in order, from the simplest math, to the strangest neuroscience, to the one thing at the end you can actually do about it. If you want real explanations for why your brain does the strange things it does, sourced, not just vibes, that's this channel. Subscribe before we start because this is one of the stranger ones. Here's the first thing to get straight. There are 2 completely different kinds of time happening whenever you ask why a year felt short. Clock time is easy. A second is a second. A year is a year. It doesn't care how old you are, how bored you are, or what kind of day you're having. Mind time is the one that actually matters to you. It's your brain's estimate built after the fact, out of memory, attention, and how much stuff seemed to happen. And here's the part that trips people up. Mind time comes in 2 different flavors too. In the moment, say, waiting in a boring line, time can crawl. But looking back at that same week, if nothing happened, it barely registers at all. It compresses to almost nothing. That gap between how slow something feels while it's happening and how short it feels once it's memory is most of what we're actually talking about when we say time speeds up as you get older. So the real question isn't why does time move faster? It's why does your brain's looking back estimate keep shrinking year after year? 4 explanations. Let's start with the oldest one and the simplest math. Back in the late 1870s, a French philosopher named Paul Janet proposed an idea so simple it's almost embarrassing. We needed a philosopher to say it out loud. A single year, Janet said, isn't a fixed size thing to your brain. It's a fraction, a percentage of your entire life lived so far. When you are 5 years old, 1 year is 1/5 of your entire conscious life. 20% of everything you've ever known. When you are 50, that same 12 months is 1/50th of your life. 2%. Same clock. Same 365 days. But to your brain, one of those years is objectively a much smaller piece of everything that has ever happened to you. And that's Janet's whole idea. A felt year keeps getting relatively smaller because the denominator, your total life so far, keeps getting bigger. People sometimes call this logarithmic time. Because if you plot it out, your sense of time roughly follows a curve that compresses more and more as you age, instead of a flat, even line. Here's a way people sometimes illustrate it. If you assume a roughly 100-year life, and you apply that shrinking fraction math, something like half of your subjectively felt life is already behind you by around age 7. Now, that number is what the model implies, not a measured fact about your actual brain. Nobody's hooked electrodes to a 7-year-old and confirmed, half done. It's math applied to an idea, not a lab result. And that's worth sitting with, because Janet's theory is nearly 150 years old, and it's never been tested the way modern neuroscience tests things. Brain scans, controlled experiments, the whole apparatus. It's a mathematical description that matches how people talk about their lives shockingly well. But matches the story people tell and proven mechanism inside the brain are 2 very different things. So think of the shrinking fraction less as a cause, more as a description, arithmetic, that captures something true about why a year feels different at 5 versus 50, without explaining why your brain works that way. Which raises the actual question. What is your brain even measuring when it decides how big a year felt? That's where the second explanation comes in, and it has nothing to do with math at all. Here's an experiment you've probably already run on yourself without meaning to. Think about a trip somewhere new, a vacation, a first semester at a new school, a big move. While it was happening, especially once you were in the thick of it, the days probably raced past. You were busy, absorbed, doing one new thing after another, never really watching the clock. But looking back on it now, that short trip can feel bigger and longer in memory than whole ordinary months back home. The science writer Claudia Hammond calls this the holiday paradox. A good, novel trip whizzes by while you're living it, yet feels long and full when you look back on it. Both things are true about the very same days. The paradox exists because your brain is running two separate jobs. One job estimates time while you're living it. The other job estimates time by counting up memories after the fact. And that second job, the memory count, is the one that actually decides how a whole year feels once it's over. So the real question becomes, what makes your brain count more memories or fewer? The answer is novelty. New, first time, never happened to you before. Your brain doesn't file away every second of your life with equal care. That would be an enormous waste of energy. Instead, it's constantly making a judgment call. Is this worth remembering in detail or not? Something novel, a new place, a new face, a new skill you're fumbling through for the first time, gets encoded richly. Lots of detail, lots of separate little memory files. Something routine, the drive you've done 500 times, the Tuesday you've already lived 1,000 times, barely gets filed at all. Your brain treats it as, seen this, no need to store the details again. So here's the mechanism. When you look back on a stretch of time, your brain isn't consulting a stopwatch, it's counting folders. More distinct memories means that felt long. Fewer means that felt short. And this is where childhood comes back in, not magic brains, just constant novelty. First day of school, first bike ride, first time a teacher yelled at you, first heartbreak. Childhood is, structurally, the most novelty-dense period most people ever live through. Every folder is thick. Every week adds a stack of new files. So looking back, that stretch of life feels enormous. Adulthood, for most people, is the opposite. You found your commute, your grocery store, your routine. The days start rhyming with each other. When a Tuesday looks like the one before it, your brain doesn't bother filing it separately. Neuroscience backs up part of this directly. The brain's ability to physically rewire itself, neuroplasticity, is highest in childhood and adolescence and gradually declines with age. That decline tracks with a reduced capacity to encode vivid, distinctive memories. It's not that your adult life has fewer things happening. It's that your brain files fewer of them as distinct, memorable events. And retrospective time is built almost entirely out of that filing system. This is genuinely one of the best supported explanations here. It doesn't rely on 100-year-old philosophers' arithmetic. It's built on decades of memory research about how novelty and attention change what actually gets stored. But even this has a limit worth naming. Most of that research covers days or weeks, maybe a single vacation. Stretching it to explain why your whole 30s felt like nothing is a reasonable extrapolation, not something measured across 40 real years. Still, novelty and memory density is probably the single biggest lever you actually have control over. We'll come back to that at the end. First, two stranger ideas. In 2019, a mechanical engineer at Duke University named Adrian Bijan published a very different kind of explanation, one that treats your brain less like a diary and more like a camera. Bijan's idea, what you experience as time passing, is really your brain perceiving a sequence of mental images, one after another, like frames in a film reel. The present feels different from the past, in his framing, not because a clock somewhere rang, but because the picture in your head just changed. New frame, new now. Bijan's hypothesis is that the rate your brain can grab and process these mental frames, call it a frames per second for your consciousness, is fastest early in life, and gradually slows down as you age. A young brain, on this view, is packing in more distinct frames per unit of clock time. More frames means more perceived stuff happening, and looking back, a longer feeling stretch of time. An older brain grabs fewer frames in that same stretch of clock time. Fewer frames, less perceived stuff, and a shorter feeling stretch looking back. Why would the frame rate slow down? Bijan points to physical changes in the aging body. The eye's rapid flicking movements called saccades, and gradual wear on the neural pathways carrying visual information from eye to brain. As those pathways take a little longer year after year, each new mental frame takes a little more real time to arrive, meaning fewer of them fit into any given stretch of clock time. Now, here's where we need to be very honest with you, because this is the point in most videos about this topic where the caveats quietly disappear. They shouldn't. Bijan is a respected, prolific engineer, but not a neuroscientist, and this idea was published in a general interest academic journal, not a specialized neuroscience journal with the scrutiny that claim would usually need. It's a theoretical argument, built from physics and physiology reasoning. Not a study where researchers actually measured mental frame rate going down in the same people as they aged over time. That doesn't make it wrong. Plenty of good science starts as a theoretical proposal before anyone tests it. But here, this one as an interesting, physically grounded hypothesis that's still debated, not an established fact about your neurons. Compare that to the memory density explanation, which rests on decades of actual experiments on real human memory. This frame rate idea is newer and far less tested, and you deserve to know the difference. So file this one as plausible, genuinely debated, worth knowing, not worth repeating as settled science. On to explanation 4 from the lab at a scale much smaller than a year. Picture a simple lab experiment. You sit in front of a screen. A gray circle flashes again and again, always for exactly the same length of time. After enough repeats without you doing anything differently, something changes. The circle. Same size, same duration on screen, but suddenly it's red instead of gray. Researchers ask people afterward, which one lasted longer on screen, the gray circles or the red one? Even though every single circle, gray or red, was up for exactly the same amount of time, people consistently say the odd one out, the red circle, felt like it lasted longer. This is called the oddball effect, and it's one of the most replicated findings in time perception research. The neuroscientist David Eagleman and his colleague Vani Pariyath proposed an explanation for why. It's about how much work your brain has to do to process something. The first time your brain sees the gray circle, it works hard to process it. Lots of neurons firing, building the representation from scratch. By the 10th, 20th, 50th repeat, your brain has essentially already got a template ready. It barely has to work at all. One leading explanation calls this repetition suppression. Predictable input costs less neural effort. When the red circle breaks the pattern, your brain suddenly has to work hard again. No template ready, no shortcut, full processing effort, right in that instant. And the theory is, your sense of an event's duration tracks how much neural effort went into processing it. More effort, more neural activity packed into that moment, and your brain reads that as this took longer. One honest caveat. The oddball effect itself is rock solid and replicated, but this particular explanation for it is debated. Newer research suggests attention, how much of it a surprise grabs, maybe doing more of the work than raw neural effort alone. So a repeated, predictable, boring stimulus gets compressed. A novel, unexpected one gets stretched inside the same actual half-second. Here's the honest caveat. This effect is measured in fractions of a second, maybe a second or two at most. Nobody has tracked someone's brain effort across a whole year to confirm the same mechanism scales up. So when any video tells you the oddball effect is why childhood summers felt endless, treat that as a compelling analogy between two timescales, not a proven, unbroken chain of cause and effect. What the oddball effect does give us, honestly, is a plausible mechanism at the neural level for something we already suspected from the memory research. Novelty costs more brain effort to process in the moment than routine does. And that effort seems to matter for how time gets tagged, both in the lab over half a second, and plausibly, though less directly proven in memory, over a lifetime. There's even a neural signal connecting the two stories. Dopamine neurons, tied to reward and motivation, fire more strongly at novel things than familiar ones, and separate research shows dopamine activity directly shifts how mice judge elapsed time. None of these four explanations stand completely alone, and that's actually the most honest place to land. Let's put them side by side. Here's the truthful summary, and it's less tidy than most videos on this topic will tell you. The shrinking fraction is solid arithmetic and a genuinely old idea, but it's a description of the pattern, not a tested mechanism inside your brain. The memory density explanation, novelty getting encoded richly, routine barely getting filed, is the best supported of the four, built on real, replicated memory research. The slowing frame rate idea is a serious, physically reasoned hypothesis from a credible researcher. But it's new, largely untested directly, and still genuinely debated among scientists. And the oddball effect is rock-solid science at the scale it was actually measured, a fraction of a second. But stretching it to explain a whole childhood is an analogy, not a proof. No single one of these four fully explains why your 30s felt like they lasted 11 minutes. Nobody in neuroscience will tell you they've fully solved this. Anyone who tells you it's simple is skipping the caveats. What they do agree on across every version of this research is the ingredient that shows up again and again. Novelty, new experience, Attention paid to something for the first time. That's genuinely useful because unlike your age or your neurons' processing speed, novelty is something you actually have some control over. So, what do you actually do with that? This is not a productivity hack section. There's no 5-step morning routine coming. It's simpler and a little more honest than that. If your brain measures a long stretch of time by counting distinct, richly encoded memories, then the lever is obvious. Give it more distinct things to encode. That doesn't mean quitting your job and backpacking across a continent, although sure, that would do it. It means breaking the sameness of routine in small, repeatable ways. A new route to work instead of the usual one. A restaurant you've never tried. A conversation with someone outside your normal circle. A skill you're bad at and just started learning. None of those need to be dramatic. They just need to be new to you. That's exactly the input your brain files richly, per the memory research from earlier. Attention matters here too. The oddball research suggests it's not just novelty out in the world. It's how much processing effort your brain actually spends on something. A new place you walk through on your phone, barely looking up, gets nowhere near the encoding a new place gets when you're actually paying attention to it. So the practical version of all this science is almost embarrassingly simple. Seek out small, real novelty and actually pay attention when you find it. Put the phone down for the new thing, at least. This won't make clock time move differently. A year is still going to be 365 days, no matter what you do. But it can change what that year looks like in your memory a decade from now, how thick the folder is when you go looking for it. That's the part that's actually yours to shape. It's a strange kind of relief, honestly. You can't out-argue the shrinking fraction, and you can't slow down your neurons on command. But you can absolutely control how many firsts you let into an average Tuesday. So the shrinking fraction, the memory density story, the debated frame rate idea, and the oddball effect at the neural level. 4 different lenses. One honest, unfinished answer and one very actionable takeaway. That summer when you were 9 didn't actually last longer in any way a clock could measure. It just left behind more to remember. This year can leave behind more too. That part's up to you, starting basically now. If this is the kind of thing your brain likes chewing on, real research, honestly caveated, no false certainty, subscribe, because that's the whole point of this channel. We'll be back soon with the next one. Until then, go do one new thing with your Tuesday.